This is my homebrew 8-bit CPU. In the previous episode, we have updated the ALU on the left here, and we've given it the ability to read and write the value in the flags register. And then we have integrated it back into the CPU, and we've given the CPU the ability to control whether the ALU writes back a result into the register file or whether the ALU's result gets discarded. Today, I want to sit down and write a new program that actually makes use of the hardware that we've added. Let's go take a look at the instruction set architecture and let's see how we can make use of the new capabilities of the ALU and this new instruction bit here. And then let's go update the assembler and write a new program. So let's take a look at the instruction set architecture document. We have wired bit number 7, which is the unused bit in the destination register operand. We've wired it up to the write enable of the register file. And so now if that bit is 0, the write is enabled, as it used to be, it's active low. But when we set this bit high, the write into the register file is going to be disabled. So we can execute instructions on the ALU which compute the result and update the flags, but which won't actually change any value in the register file. The result will just be discarded. Then we've also added the FSWAP ALU operation, which has ALU opcode 1100, and this should now allow us to define a few new operations. Let's start with an FSWAP operation. This one is pretty simple. It doesn't have an RS operand, so we set all those bits to 0, and it just has a destination operand, which we read and then write into the flags register, and at the same time we take the contents of the flags register and we write that back into the RD operand. So with this FSWAP instruction, we can exchange the current value in the flags register with the current value in one of the processor's normal registers, which is going to be pretty handy. Now that we can control whether the ALU result gets written back into the register file or not, one cool thing we can do is we can take the subtraction operation and disable the write back into the register file. And the effect that this will have is if RD and RS are the same, the result inside of the ALU is going to be 0. So the 0 flag is going to be set. So you can consult the 0 flag to see if both operands had the same value, because if the subtraction returned a 0, both had the same value. But you can also look at the sign flag, the carry flag, or the overflow flag to figure out which side of the subtraction, RD or RS, was greater than the other. So this can basically be used to compare the value in two registers and then update the flags accordingly without actually changing any of the values in the register file. And once we have operations that can make use of the flags to make decisions, like a conditional jump or maybe a conditional move, you can actually use that to compare two things in the register file and then take an action based on what the result of that was. I'm going to use an exclamation mark here in the hexadecimal encoding to show that the uppermost bit actually has to be set in the destination register. So we'll get rid of this later on once we have proper instruction encoding and decoding. Another thing we can do is we can do an AND operation between two registers and then not write back the result into the register file. This can be pretty useful. For example, if you AND a register with itself, it's basically going to be a no op. It's not going to do anything. It's just going to produce the register value itself as an ALU result. But the ALU will update its flags based on that value. So if the register was a 0, the 0 flag will be set. Or if the register had its sign bit set, the sign flag will be set. So such an AND that doesn't write back into the register file can be used to test whether a register is 0 or whether the sign bit in a register is set. But since this is just a plain old AND instruction, you can also use this to check if certain bits in a register are set by storing a bit mask into one register and then ANDing that with another register, the register you want to actually bit test. So this is going to be a very useful operation as well. So that's 3 new instructions for our CPU that are going to be very handy. Let's go and update the assembler accordingly. First, let me add this to the assembler test file, so we have something that fails and we can fix. And as expected, the assembler isn't happy with the new instructions because it has no idea what to do with them. So let's go fix that. Let's update the assembler. First of all, we need new opcodes for these instructions. Then we also want to be able to parse them properly. Then once they're parsed, we also want to be able to print them back out. And finally, the assembler also needs to be able to encode these instructions into the corresponding bit pattern. So compare is basically like subtraction, but we're additionally also setting this bit number 7 in the instruction, which is what disables the write back into the register file. Then test works the exact same way, but we're using the AND ALU operation. And finally, FSWAP is pretty straightforward. It just has a destination operand and it has its own dedicated FSWAP ALU operation. And I think that's all we need to do in the assembler. Let's go see if the test program works. And yeah, that seems to work. If I scroll up a bit, you can see these new compare, test, and FSWAP instructions in the output here with the appropriate encoding. Alright, so we have new instructions in the instruction set architecture and the assembler knows how to emit them. Let's go write a new program and let's try to make some use of those new instructions. I'm just going to copy over an old program such that we have the register clearing sequence in there already. So for starters, let's maybe try out the individual flags. Let's start out with the 0 flag. This should be pretty simple. I think what we can do, since all the registers are cleared to 0, is just to add 2 of those 0 registers and then observe if the 0 flag is set in the ALU. And then to try the opposite, let's load a 1 into register R0 and then do the same addition, and then check if the 0 flag disappears. And while the registers are still kind of clean, let's maybe try flag swapping. Let me load some value into register R0 and then let's see if we can flag swap that value into the flags register. At this point, we expect the flags register to be basically the lower 4 bits of register R0 and to have register R0 updated to match whatever's in the flags register. Now that the flags register is set to a 1101, let's try to flag swap into a different register of the CPU and see if we can pull the flags back out. R1 is 0 at this point, so we expect the flags register to be set back to 0, but R1 should be updated to contain the current state of the flags, which was 1101 at this point. Okay, that should be a quick first check of flag swapping. Let's try the sign flag, which is pretty trivial. Let me load the number 128, which is just the topmost bit set, into R0, and then let's clear R1 back to 0. And then let's add these 2 numbers, which will basically produce 128 as a result, but we expect the sign flag to be set since the sign bit of the result, bit number 7, is going to be set. Okay, now to the more complicated things. Let's try to test the overflow flag. And I think what we can do is we can just try a few additions with different combinations of left and right hand side operands. And if the sign of the output flips in comparison to the operand, we expect the overflow flag to be set. For example, let me add 20 and 22, and we expect to see 42 as a result and no overflow flag to be set, because if we interpret numbers as signed, the inputs were positive and the result 42 also fits into 8 bits and is positive, so no overflow occurs. Let's try the same thing with a negative number. Let's add -20 and -22, and we expect to see -42 in the output, and again no overflow because the 2 inputs had the sign bit set, so they were negative, and the result also has the sign bit set, so it's also negative. In this case, we also expect the sign bit to be set because the result is negative, and because of how the subtraction works, we also expect to see the carry flag to be set. Now let's try a case where we actually do produce an overflow. For example, we could add the numbers 100 and 101, and the result would be 201. But because 201 doesn't fit into an 8-bit register, if you interpret the register as a signed number, it will actually read as a -55. So we would detect this as an overflow because the sign bit of the inputs was 0, they were positive, but the sign bit of the result now is a 1, it's negative, and this is unexpected, some overflow occurred. So in this case, we do expect the overflow flag to be set, and we also expect to see a sign flag because the sign bit of the result is set, it's negative. Let's try the same thing with negative numbers. Let's try to add -100 and -101, and you'd expect to see -201 in the result, but again -201 is too negative to fit into an 8-bit register if you interpret it as a signed number. So the overflow flag would be set because the input operands had the sign bit set, they were negative, but the result doesn't have its sign bit set, so it reads as a positive, which is an overflow. And then finally, let's maybe try to produce the most negative number we can without producing an actual overflow. So let's add minus 28 and minus 100, which should result in minus 128, which is indeed the most negative number we can represent. And in this case, we do not expect to see the overflow flag to be set because both inputs read as negative because the sign was set, and the output also reads as negative because its sign bit is set. And we can do a similar thing for the most positive number we can represent. Let's add 27 and 100 to result in 127, which is indeed the most positive number we can represent in 8-bit sign-bit arithmetic. Okay, pretty sweet. That should actually cover quite a few of the overflow corner cases. Now we also have this new compare instruction, which compares the value in two registers, basically performs a subtraction and then doesn't write the result back into the register file. So let me load the value 20 into R0 and 22 into R1. So to get started, let's maybe compare R0 with itself. And so since compare is actually subtraction internally and both sides of the subtraction were identical, we expect the 0 flag to be set because the result is going to be 0. Another way to look at this is if we do a comparison and the 0 flag is set, this implies that both sides of the comparison were actually equal. But on top of that, because how subtraction is implemented, we're also going to see the carry flag be set. And if you rummage around the documentations for the 6502 or the x86 processor, you can actually look at the carry flag to figure out which side of the comparison was greater or equal to the other and which one was less. So in this case, a carry flag being set implies that the left-hand side was greater or equal to the right-hand side, which is correct because we compared R0 with itself, and it is indeed greater or equal to itself. In fact, it's equal to itself. Then let's maybe compare R1 and R0. In this case, the value is non-zero. We're basically computing 22 minus 20. So the ALU's result is going to be the number 2. So the 0 flag will be cleared. And in this case, the 0 flag being not set implies that the two operands to the compare were non-equal. And because of how the subtraction works, the carry flag will be set. And the carry flag implies that the left-hand side, the 22, was greater or equal than the right-hand side, the 20, which checks out. Let's also try it the other way around. Let's compare R0 and R1. In this case, we again don't expect the 0 flag to be set because we're basically computing 20 minus 22. So the result is going to be minus 2. And so the 0 flag is not going to be set, which will imply that the two sides were not equal. And because of how subtraction works, in this case, the carry flag will not be set. And this implies that the left-hand side is actually less than the right-hand side. It's not greater or equal. And this checks out. The left-hand side is 20, which is indeed less than 22. And if you look at this, you can clearly see how you can run a comparison on two registers and then look at the flag to derive all kinds of comparison results from that. If you're just interested in equality, you can just check the 0 flag to see if it was equal or non-equal. Or if you want to know whether it's greater or equal, you can just check the carry flag being 1. Or if you want to see whether the left-hand side is less than the right-hand side, you can just check the carry flag being 0. But you can also do the opposite. You can check if the left-hand side was greater than the right-hand side. And to do that, you'd have to first check if the carry flag is 1, which would mean that it's greater or equal. But then you also check that the 0 flag is 0 in this case to exclude the equal case. And that will basically give you the indication of whether the left-hand side was strictly greater than the right-hand side. And you can do a similar thing if you're interested in whether the left-hand side is less than or equal to the right-hand side. You would check if the carry flag is 0, which is the less case, or if the 0 flag is 1, which would be the equal case. And then together they will combine into a less than or equal. And there's actually a fairly compact piece of hardware that you can build that checks various interesting combinations of these flags, which we're going to do in a future episode. But for now, I think this suffices as a taste of what we can do with the flags. In addition to this comparison, we also have a new test instruction where we can test a register for 0 or non-zero efficiently, or we can also do bit testing. So let me load a few bit patterns into the registers. First up, let's actually test register R3 with itself, because R3 is still 0 at this point. So we're ANDing 0 with 0, so the result is also going to be 0, and correspondingly the 0 flag is going to be set. And in this case, this indicates that the register R3 was indeed 0. We can also do the opposite. Let's test R2 with itself. And in this case, we expect the 0 flag to not be set because R2 is a non-zero register. We're ANDing it with itself, so basically just forwards the value in R2 to the ALU result. And then the ALU looks at the resulting bits, which are non-zero, and correspondingly doesn't set the 0 flag. So the 0 flag being 0 here indicates that the value in R2 is non-zero. And so you can see how this can be useful if you are running some algorithm and you're doing some computation, and at some point you actually need to check if some random value in a register is 0 or is non-zero. You can just feed that register into the test instruction, which is going to update the flags to the appropriate values. It's going to set the 0 flag to 1 or 0, and then you can do whatever you want with that information. You might be able to do a conditional jump or some move or something along those lines. And now, since test is actually an AND operation in disguise, we can do some interesting bit testing. For example, let's test register R0 with R1, and the result of that AND operation is going to be non-zero in this case, and so the 0 flag is going to be not set. Another way to look at this is to look at register R1 and seeing that it only has bit 2 set. And if we AND this with any other register, it's basically going to test whether bit 2 is set in that other register or not. And so in the case of testing R0 with R1, basically ANDing the two registers together, the result being non-zero, the 0 flag not being set, implies that bit number 2 in register R0 was set. And let's try the other case. Let's test R0 with R2. In this case, the result is going to be 0 because register R2 only has bit number 1 set and register R0 does not have bit 1 set. So if we AND the two together, we actually get a 0 as a result. And so in this case, the 0 flag being 1 implies that bit 1 in register R0 is not set. And I think you can see how this can be useful in practice. You can not only test an individual register to see if it's 0 or non-zero by ANDing it with itself, but you can actually use two different registers to perform a form of bit testing. Alright, so that's basically all the new flags and all the new instructions tested. But I think it would be cool to try and do something a little bit more ambitious that we haven't done in the past. And I think what we can do is, now that we have these flags available and we have the flag swap operation, and we can basically take the flags and perform some computation with the actual bit pattern in the flags, I think we can implement a very primitive form of conditional branching, conditional jumps already without having actual support for that in the CPU. And I think what we should be able to do is we should be able to load two values into two registers and then perform multiplication, basically by performing repeated addition in a loop. So let's try that. Let's maybe load the value 5 into R0 and the value 29 into R1. And then we're going to try to compute 5 times 29, which should be 145 at the end. And so I think we need a kind of loop here. And what we want to do in this loop, I think, is we want to take one of the inputs to the multiplication and add it into the result, and then decrement the other input of the multiplication by 1. So for example, we could take the value in R1 and add it to the result register, and then decrement R0. In this case, R3 would be our result register, and this would repeatedly add 29 to the result register until R0 has dropped all the way to 0. So ideally this would add 29 to R3 5 times in total. And now the interesting thing here is, after this subtraction, the 0 flag actually indicates whether R0 has reached the value 0. Because R0 starts out at 5 and we keep subtracting 1 from it, so it keeps decrementing. And as soon as this reaches 0, the 0 flag will be set. So at this point, after the subtraction, it would be cool if we could actually somehow extract the 0 flag from the ALU and then try to decide whether we want to do this jump back into the loop or whether we want to skip that jump and exit the loop. To do that, I think we want to do an FSWAP after this subtraction to get the current state of the flags into a processor register, where we can do some arithmetic on it. After this flag swap, R4 will contain a concatenated version of the overflow flag, the sign flag, the 0 flag, and the carry flag. And the thing we're interested in is the 0 flag. We want to see if the result was 0 or not. So let's try to isolate the 0 flag. Let's try to manipulate R4 such that it only contains the 0 flag at the bit position 0. An easy way to do this is to first shift this to the right, which will drop the carry flag, and the 0 flag will be all the way at the bottom in the least significant bit position. And then we can AND it with the value 1, which happens to be in register R2, and that will basically zero out the entire register except for the lowest bit where the 0 flag is. So at this point, R4 just contains the 0 flag. So this is a pretty good starting point. We have the 0 flag in register R4. And I think we can use the 0 flag now to compute a relative jump offset. I want the relative jump to just jump to the next instruction, basically like a no-op if the 0 flag is not set, if we're not done with the multiplication. Or I want the relative jump to skip the next instruction if the 0 flag is set, which will basically break out of the loop. Because this jump would then decide whether we actually do this jump relative with immediate back to the loop if we continue looping, or if we skip that jump back and if we break out of the loop in that way. If you remember how relative jumps work, they basically take the current program counter value and then they add the value in R4 in this case, and this is where we jump to. If R4 contains a 0, we wouldn't jump anywhere, we would just be stuck in place because we take the current PC, add nothing to it, and we would basically stay where we are. The instructions are 2 bytes each, so if R4 is set to the value 2, to jump ahead 2 bytes, this is equivalent to just stepping to the next instruction, and the jump relative with register would behave just like a no-op. And since instructions are 2 bytes each, we can actually skip the next instruction by jumping ahead not 2, but 4 bytes, which would jump over the next instruction. So to summarize, if R4 is 0, we just get stuck in place here. If R4 is 2, we just step to the next instruction, we just go here as if the jump were a no-op. And if R4 is set to the value 4, we would actually skip an instruction and jump right here. So to summarize, if the sign flag is not set, we want to jump by 2. And if the sign flag is set, we want to jump by 4. That doesn't sound too hard. I think what we can do is we can take the value in R4 and add a 1 to it first. That will basically set R4 to the value 2 if the 0 flag is set, or the value 1 if the 0 flag is not set. And then we can shift R4 to the left by 1 position to basically multiply this by 2, such that R4 will be set to the value 4 if the 0 flag is set, or 2 if the 0 flag is not set. And this is exactly the value we're after. If the 0 flag is set, we're done with the multiplication. R4 is going to be 4, so this will skip out of the loop. But if we're not done, if the 0 flag is not set, R4 will be set to 2. So we're just stepping to the next instruction, which is this branch backwards in the loop. So we continue the loop. And so after we exit out of this loop, we expect the result register to contain the value 145, which is 5 times 29, because we've basically added 29 to this register 5 times. And at this point, let's just clean up the register file back to all zeros and halt the processor. And the only thing left to do is we actually need to replace this loop here with an actual jump offset, because the assembler doesn't yet support labels in the program. That's something we'll probably want to add sooner rather than later, because it's going to be very useful once we develop more complicated assembly programs. So these are 8 instructions here. That means we have to jump backwards by 16 bytes. All right, that's it. If all works out, this will actually do a multiplication for us. And the really cool thing here is that this is the first time that we're making a control flow decision, whether we should exit the loop or not, based on data that is in the registers. So we have a first case of data-dependent control flow in the processor. And this is going to get a lot simpler in the future once we have conditional jumps. But it's interesting to see that just by having a flag swap operation, by being able to pull flags out of the ALU and then perform regular arithmetic and logic with them, we can get pretty close to a conditional branch. Just a lot less convenient, arguably. Let me assemble this program into a binary. And then let me get the program memory out of the CPU, write this new program to it, and then get it back in there. And then we can do a test and see if all of this works as expected. So let's see if this works. First, we're going to clear the registers. Next up, we're testing the 0 flag. We're adding register 0 and register 1, which are both 0. So the result is 0, and indeed the 0 flag is on. And when I hit the clock, the 0 flag gets stored in the flag register. Now we're loading a 1 into R0. And we're adding R0 and R1 again. This time the result is 1, so the 0 flag is not set, and when I hit the clock, the 0 flag gets cleared in the flag register. Next up, we're going to test the flag swapping. We're loading a pattern into R0, which works. And now we're doing a flag swap operation, which is a new thing. What we're going to do is we're going to swap the value in register R0 with the flags register. And at the ALU, you can see that the FSWAP operation is selected, and the decoder appropriately decodes this into the all ones truth table, which is a special code which we're not using, which the logic PLDs down here convert into an FSWAP signal that drives the swapping multiplexers up here. And so when I hit the clock, this value will move into the flags register, and the 0, which is currently in the flags register, will move into register R0. Which is exactly what happens. This is the value that was in R0, and this is the value that was in the flags register. Now we're going to do another flag swap, but this time with register R1. So we're expecting to see the contents of the flags register to appear in R1, and the 0 that's currently in R1 to appear in the flags register. Which is exactly what happens. The flags register became 0, and the register R1 contains what the flags were before. So that seems to be working. Pretty cool. Now we're going to test the sign flag, which is pretty straightforward. We're loading 128 into R0 and 0 into R1, and then we're just adding the 2. And over at the ALU, you can see the result is 128 as you would expect, and the sign bit is set, and correspondingly the sign flag of the ALU is set. And when I hit the clock, the sign bit gets stored in the flags register. Next up, we're going to test a few cases of the overflow flag. So we're loading 20 into R0 and 22 into R1. And now we're adding the 2. And indeed, this is the 42 that we would expect as a result. And the overflow flag is not set because 20 plus 22 is indeed 42, and there's no ambiguity. Let's do it with negative numbers. Let's load minus 20 into R0. And minus 22 into R1. And now we're going to add the 2 values again. And over at the ALU, you can see that we have 2 negative inputs. The sign bits for the left and right hand side are both set, and the result is also negative because the sign bit is set. And because there was no unexpected flipping of the sign bit, the overflow flag remains cleared. Now let's try a case that will overflow. We're loading 100 into R0. 101 into R1, and now we're doing the addition again. And this time, the left and right hand side are both positive, the sign bits are cleared, but the result is so large that the sign bit of the result becomes set. And indeed, this is unexpected. This result here is 201, as you would expect if it's an unsigned number. But if you assume that these are signed numbers, this is actually the number minus 55. So an overflow happened, a signed overflow happened. And correspondingly, we are setting the overflow flag here. Now we're going to try it the other way around. We're loading minus 100 into R0 and minus 101 into R1. And now we're doing the addition again, and the left and right hand side inputs of the ALU are both negative. The sign bit is set, but the result doesn't really fit. The result overflows. The sign bit of the result is no longer set. And indeed, we set the overflow flag appropriately to indicate that this happened. Now let's try a combination that will actually fit. For example, we're loading minus 28 into R0 and minus 100 into R1. And we're adding the 2. Both sides of the input are negative, the sign bits are set, and the result is also negative, the sign bit is set. And this is in fact the most negative number we can represent in an 8-bit machine. This is minus 128, as you would expect. And there's no ambiguity, no flipping of the sign, so the overflow flag stays cleared. Let's do the same for positive numbers. We're going to load 27 into R0, 100 into R1, and we're doing the addition again, and again, the left and right hand side are both positive. The result is also positive. It's 127. It's the largest positive signed number that we can represent in 8 bits, and correspondingly, the overflow flag stays cleared to indicate that there was no unexpected overflow happening here. Pretty cool. Now we're going to do a few comparisons between registers without actually changing the registers. So we're loading the value 20 into R0 and 22 into R1. And now we're going to do a few comparisons. We're using this new compare instruction that we've just created. And first up, we're just comparing R0 with itself. So both operands are the register R0. And the comparison inside the ALU is actually a subtraction, which you can see here, the ALU operation is set to subtract. And the ALU does its thing, does its subtraction. It produces 0 as a result, as you would expect, because we're subtracting 20 from 20, so the result is 0. And correspondingly, the flags are getting updated appropriately. The carry flag is set because of how the subtraction works, and the 0 flag is set because the result is 0. But now, because this is the compare instruction, and we actually have bit 7 of the instruction set, notice that none of the registers is selected for writing. The ALU does produce its result and puts it onto the right data bus, but the register file is disabled. It will not update itself. And so conveniently, this allows us to compare registers and store the corresponding flags in the flag register, but actually not destroy what's in the registers themselves. So if I hit the clock, the flags get updated in the flag register, but none of the registers actually changes. And this is very convenient. We can look at the flags, and the flags will tell us how the two registers compared. Notice that we actually compared R0 with R0. So the 0 flag being set indicates that the two were equal. They subtracted to a 0 result. And the carry flag here, it can actually tell you which one of the sides was greater. And if the carry flag is set, this indicates that the left-hand side was greater or equal to the right-hand side. Now we're going to do a slightly different combination. We're going to compare R1 against R0. Again, in the ALU, this turns into a subtraction. And because we're comparing 22 and 20 with a subtraction, the result is no longer 0. So the 0 flag is off, which basically tells us that the two inputs we had, the two registers we're comparing, are not equal. And the carry flag is set, which indicates that the left-hand side, the 22, is greater or equal than the right-hand side, the R0, which is also correct. Now we're going to flip it around. We're comparing R0 and R1. Again, because 20 and 22 are not the same, the subtraction is going to produce a non-zero result, which is the case here. So the 0 flag is not set. But now, because of the way the subtraction works, the carry output of the adder is actually cleared, and the carry flag is not set. And this indicates, with the 0 flag being cleared, that the two were not equal, and with the carry flag being cleared, that the left-hand side, which was the 20, is actually less than the right-hand side, which was the 22. So that seems to be working. And again, if I hit the clock, the flags update, but none of the registers actually get changed. Next up, we're going to try out the new test instruction. First, we're going to load a bit pattern into R0, R1, and R2. And first up, we're going to test register R3 with itself, and R3 is 0. And what the test does is, at the ALU, it actually translates into an AND operation, and the decoder properly decodes this into the AND truth table, and it will produce some interesting flags. And so we're taking the value in R3, which is a 0, we're ANDing it with itself, produces a 0, and the 0 flag is getting set. And the 0 flag indicates that indeed R3, the register we're testing, is 0. So if I hit the clock, the 0 flag in the flags register is set, which tells us that the register was 0. We can also do this on a non-zero register. Now we're testing R2 with itself, and ANDing a value with itself, so R2 and R2 is the same as just R2, so it's not going to do anything in the ALU, but it's going to produce the value of R2 as an intermediate result here after the adder. And this is what we're using to update the flags, and because this is non-zero, this R2 value is non-zero, the 0 flag is actually cleared. And so when I hit the clock, the flags register is updated appropriately, the 0 flag is cleared, and this indicates that the register R2 we were testing was actually non-zero because the 0 flag was cleared. And quite conveniently, because this is an AND operation between two registers, we can use it to bit test a value. Let's look at this for an example. We're testing R0 with R1. So what we're doing is we're taking the value in R0, which has the 2-bit set, and we're ANDing it with the value in R1, which is just the 2nd bit set. Now correspondingly, the 0 flag is not set because the result is non-zero, and this indicates that bit 2 of register R0 was set. And here's a different example. We're testing R0 with R2. R2 has bit 1 set, which happens to not be set in register R0. So essentially the AND operation between these two registers is a 0 because they had no bits in common. And correspondingly, the 0 flag is set, and when I hit the clock, the 0 flag is going to get stored in the flags register. So this is a very convenient way to test whether some bits in a register are set. If you have a bit mask in another register, you can just call test on the two registers, and the result will be 0 if they shared no bits, so if the bit mask you had set was 0 in the other register, or the result will be non-zero if they had a few agreeing bits. This will be stored in the 0 flag. Alright, and now to the grand finale. We're going to do multiplication by repeatedly adding numbers together. This isn't the most elegant way to do multiplication, but it is an easy way that allows us to show off what we can already do with these flags. So let me load the number 5 into R0, 29 into R1, and the value 1 into R2. And now the goal is to multiply 5 and 29, which should come out as 145. And we're doing this in a loop by repeatedly taking the 29 and adding it to register R3, which is going to hold our result. And the idea is to do this addition repeatedly and counting down register R0. And as soon as register R0 hits 0, we know that we've added 29 to the result 5 times. So this will be the same as multiplying 5 and 29. So let's step through this and let's take a look. So we're adding 29 into R3, which works. Then we're subtracting 1 from register R0. This becomes a 4. And now the interesting thing is that in the flags register, the 0 flag is not set because the result of the subtraction, the 4, was non-zero. And now we're trying to extract that. We're doing an FSWAP into register R4, so this will copy the flags register into R4. Now the 0 flag is bit 1 and the carry flag is bit 0, and we want to isolate the 0 flag, so we're right shifting this number by 1, which now makes the 0 flag be all the way at the bottom. Now we're ANDing it with 1 to isolate the 0 flag in case some other garbage flags are set. Now we're adding 1 to that number, which comes out as 1, and now we're left shifting this number by 1 position. And that effectively multiplies it by 2. And this is our clunky way to compute a relative jump offset. If the 0 flag is set, this number would now be 4, and if the 0 flag is not set, this number is 2, as it is now. And so we're now doing a relative jump with register by using this register. And if the value is 2, this is effectively just stepping to the next instruction in the program, which is 2 bytes ahead. But if the result were 4, we would actually be skipping over an instruction. So we're doing a relative jump by 2, so this is just the same as advancing to the next instruction, which works. And the next instruction here is a relative jump backwards by 16 bytes, I think. So this will take us all the way back to the beginning of the loop where we're doing this addition again. And indeed, this is the add operation. So let me step through this pretty quickly until we come to the point where register R0 becomes 0, which is where the interesting things are going to happen. So we're adding the 29 into the result register again. We're decrementing R0. It becomes 3, it's non-zero. We're F-swapping into R4. Right shifting, isolating the 0 flag, adding a 1, and then we're left shifting. We're doing a relative jump again, which takes us to the jump backwards to continue the loop. And this is the addition. So even faster now, adding 29 to the result again, decrementing the counter. Turned out to be 0, so we're now doing a jump backwards again. So we're adding 29 to the result again, decrementing R0, which happens to be non-zero, so we're going to do another iteration. F-swap, shift right, and add, shift left, and then skip. And now because we didn't skip anything, we're going to go back and another addition, so we're adding 29 into the result again. We're decrementing our 0, which is a 1, and after decrementing this will actually become a 0. And now the 0 flag is on, which wasn't the case before, so pretty sweet. Now we're doing an FSWAP into register R4, which means this flag register content is going to appear here in R4. Notice that now the two bottommost bits are set, not just the bottommost one. This corresponds to the 0 flag and the carry flag. So we're going to do a right shift. This brings the 0 flag to all the way at the bottom bit 0. Then we're ANDing with 1 to isolate the 0 flag. Now we're adding 1. This turns this into a 2. And now we're doing a left shift by 1, which is essentially a multiplication. And this is now our jump offset. Because we have reached 0 here and the 0 flag was set, we were able to influence how we make this computation work here. And it's now a 4 instead of a 2. So when we do this relative jump where we're at right now, we're not only going to jump to the next instruction, which would be the jump by 2, we're going to jump ahead another instruction. We're actually going to skip an instruction, which is 4 bytes ahead in the program. And so indeed, if I hit the clock, we have now skipped that backwards jump to continue the loop. And we're now at the end of the loop after the main loop body. And indeed, the computation is now over. Our 0 went all the way down to 0. And if you take a look at register R3, which is our result register, it now reads as 145, which indeed is 5 times 29. So that worked like a charm. And this is really powerful. We didn't do a fixed number of iterations through the program. This was actually the first time where we did a conditional jump in the program. We took a value in a register and produced some flag, and with the FSWAP and some bit shifting and extraction of bits, we were able to look at the 0 flag in the ALU and make a decision based on that 0 flag. Do we want to continue looping, or do we want to exit the loop and continue on? And the number of iterations we did isn't hard-coded in the program. If we loaded a different value into register R0, the program would have just done more loop iterations until R0 became 0, and only then exit out of the loop. So this is getting very, very close into Turing completeness territory, because now we can actually affect the control flow of the program, which instructions get executed, based on the data that is in the registers. And this is afforded to us by this flag swap instruction, which allows us to take the flags and just treat them as regular plain old data and extract one of the flags that we're interested in, and then mess around with a compute jump offsets based off of that, and then do a relative jump with that. All right, and with the registers cleared up again, this is the official end of the program. So we're getting very close to actually having the ALU done. I don't think there's a lot more to add to this. We have flags available, we have a flag register, we can swap flags in and out of that register pretty efficiently. We can do addition, shifting, logic operations, and we can combine that with the register file and the program counter to do all kinds of interesting jumps and interesting behaviors as we execute a program. I think in the next episode, it would make sense to look a bit more into how we can do more of this conditional behavior, where the program actually looks at some data in the registers and then makes a decision about what to do. And by using the flags and shifting them around to compute a jump offset, we were able to already implement a sort of poor man's conditional jump in this very simplistic CPU. Another feature that would be pretty useful to have, I think, is a conditional move, where we actually pick one of the two inputs to the ALU to produce as a result, depending on some condition of the flags register. And so building up a concept of condition codes where we look at a flag or multiple flags to interpret the flags register as a sort of condition for jumping or for doing a conditional move would make the CPU a lot more powerful. And I think that's what we might want to look at in the next episode. All right, this is pretty exciting. I can't wait for this to happen and for this to get even more powerful and kind of finish out the ALU building here. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.